Okay, so it's a great pleasure to welcome you back to the John Fox annual LIFD lecture. As I said earlier, and you may have noticed, this lecture series is on the theme of geophysical and astrophysical flows. And when I thought, who should we get to give the John Fox lecture, really there was only one person that I thought would be great for this. So it's a great pleasure to welcome Lucie Green, who I've known for let's not go into how long we've known each other, quite a long time. So Lucie is Professor of Solar Physics at UCL's MSSL, and she works on the origins of coronal mass ejections, so you'll probably find out what a coronal mass ejection is later on in the talk. And of course, Lucie's very active in science communication. She's been a presenter on BBC's Sky at Night and Stargazing Live, and she was the recipient of the Royal Society's Kohn Award for Excellence in Public Engagement and the Institute of Physics Lise Meitner Medal and Prize for Distinguished Contributions to Public Outreach. So it's a real pleasure to have Lucie here to give us the John Fox annual lecture.
Thank you very much. Thank you. So thank you very much. It's a great honour to be here joining you this evening. So thank you very much for the invitation to come up and talk about my favourite object, which of course is the sun. That's a giveaway on the screen behind me. So you will find out what coronal mass ejections are if you don't know already. And what I want to do is kind of bring alive the sun as a magnetised fluid, which of course everybody in this hall is interested in. So I want to give you a bit of an introduction first of all into who I am, where I work, just in case you don't know of the department I work in at UCL, and then have a look at the sun. And I am an observational solar physicist, so this talk will be full of images of the sun taken with the various spacecraft that we have operational at the moment, so I hope that's okay. So, my name's Lucie Green, I work at UCL, and I work in a place called the Mullard Space Science Laboratory. So even though we are a department of UCL, which is a London university, our department is out in the Surrey Hills. So we're kind of a quirky place because there are around 200 of us in this department doing space science research covering galaxies, black holes, solar system science, planetary science, but also building instrumentation. And so we often get members of the public coming to visit us because they're very interested to see what happens in our building, which looks like this. So this is a picture of where I work, not very London. We're out in the Surrey Hills. So we work in what is called Holmbury House on Holmbury Hill, which is in between Guildford and Dorking, for any of you who know the Surrey countryside. So it's a really fantastic place. We have rare breed cows that use the grounds that we own. There's about 30 acres on this site, so they sometimes escape and come up to the house. This was a picture taken by Steph Yardley when she was with us at UCL. So from rockets to cows, you never quite know what you're going to encounter when you come into work in the morning. My office, I'm lucky to say, is one of the ones in the front of the building. So I have this fantastic view over the Surrey Hills looking down towards the South Downs, and it's a really nice place. So if you're ever passing by Surrey, come and visit us. You're very welcome to come and have a look around. And the reason that we are based out in the Surrey countryside goes back really to the origins of the UK space programme. So at UCL, there was a physics department which was led by someone called Harry Massey. And I think he's a name that's not well enough known of in the UK. Maybe put your hand up if you've heard of Harry Massey. 1, 2, 3, maybe 4 people. Okay. So Harry Massey was head of physics in the 1950s at UCL. But he was a very well-connected person, working across the Royal Society, working internationally. And he was called by the Ministry of Supply in 1953 and offered the use of rockets that were left over after the Second World War for upper atmospheric research. He said yes, and the story goes that with that yes came the birth of the UK's rocket programme. Here's a picture of Harry Massey in his office. Like any good head of department knows, you're surrounded by paperwork, totally buried. So he was actually an Australian, which also gave the links between the rocket programme and the launch site in Woomera in Australia. So from the early days, The rocket program began with the Skylark program, which is a picture here showing a couple of people at MSSL in the actually the potting sheds, which are where our mechanical workshops are, working on a nose cone of a Skylark rocket. And so UCL, as well as the other UK universities who came together to make this program a success, had their first rocket launch in 1957. And it was such a successful program that the rocket group at UCL grew very rapidly. So by the time we got into the early 1960s, there was a need for more space. And a donation came from the Mullard company who made valves, now owned by Philips, to buy a new property. And that's when the feelers went out into the Surrey hills to see what kind of building might be available to house this growing rocket group. And again, the kind of urban myth that I've been told is that the people who were overseeing the group at that time and what then became the Mullard Space Science Laboratory were interested in being away from UCL, away from the bureaucracy, in an environment where they could get on with the task at hand with the people needed to make that a success. And that very much underpins our kind of culture today, that we want to have everybody in the same building who can design, build, test, space instrumentation, and then analyse the data that comes back from that instrumentation too. And so today we're working, as you all know, in the UK, we're part of the European Space Agency, but we work a lot with the Japanese Space Agency. We have a mission coming up with the Chinese Space Agency that's launching very soon. So it is a very international program, but I think everybody in this room will know that. But going into space then means that we can not only do our upper atmospheric research, but we'll have access to the universe in a range of wavelengths that are otherwise absorbed by the atmosphere of the Earth. So, for example, when we're looking at the sun, we can go from our white light continuum images of the surface of the sun and go into wavelengths that don't make it through our atmosphere, like extreme ultraviolet light and into the X-ray part of the spectrum. So as an observational solar scientist, these are very much the kind of data sets that I work with. And these ones in particular come from a couple of missions, a NASA mission called the Solar Dynamics Observatory and a Japanese mission called Hinode. So all of these images and data sets are freely available. Anyone can access them, either for science or if you want them for public engagement, you can do that too. And I can show you how to get those data sets easily accessible. So the era began then in the space age, in which we were not only able to look at the sun using different wavelengths of light, but also use techniques that are quite challenging on the Earth. And there's a particular technique that we use a lot in solar physics to study these coronal mass ejections, these eruptions from the sun, and that is to create an artificial solar eclipse. So the moon does this perfectly once every year and a half or so, and we want to try and recreate that with our telescopes by putting a disk in front of the bright photosphere of the sun to block out that intense light and then enable us to see the more diffuse and much, much weaker light that's being scattered from the gases in the atmosphere of the sun. So when the space age began, these coronagraphs, these telescopes that occult the sun, were launched and put into space. The first one being on a NASA mission called Orbiting Solar Observatory. It does what it says on the tin. It was a solar observatory put into orbit, and that was launched in the early 1970s. So this carried on board a telescope that would occult the sun and allow us to see the atmosphere. The data were kind of primitive compared to what we have at the moment. So on the right-hand side, you can see some snapshots of some of that early data. It probably doesn't look very identifiable to you. So the sun is occulted and is in the top right-hand side of each of those boxes. So we're just looking at part of the atmosphere of the sun, not the whole atmosphere around it. So you can see the kind of black disk in the top right-hand corner. And what you also may be able to see is a kind of fuzzy white structure that appears most obviously by the bottom left-hand image. And this is actually a coronal mass ejection leaving the sun. But at the time, these eruptions weren't known about. And when the technicians saw these images coming down from the spacecraft, they thought they were problems with the camera rather than a real event happening in the atmosphere of the sun. So initially they were dismissed. But on careful examination, it was realized that yes, this is a real thing that the sun is doing. And this kind of new era began where it was understood that the sun erupted huge amounts of magnetized plasma into the solar system. Some don't achieve escape velocity, yet somehow they're driven out into the solar system. Others do. So they can have a range of speeds from hundreds to maybe 2,000 or 3,000 kilometers a second. So carrying billions of tons worth of plasma at millions of kilometers an hour, requiring a huge amount of energy to escape the sun, but also forces to enable these structures to leave the sun too. And coronal mass ejections became the focus of the research I do. They are fascinating, they're highly relevant to our lives because when they come towards the Earth, if they reach the Earth's magnetic field and interact with it, then they can drive what we call space weather events, which on the one hand might be great displays of the northern lights, but on the other hand might be a kind of knock-on series of effects where we have electric currents, electric fields set up in our electricity distribution networks, or changes to the upper atmosphere that impact our propagation of high-frequency radio waves, for example. So there's a whole area of research now around space weather and how the sun creates and controls that. So to come then to the kind of modern era and look at the sun and its eruptions as we do now, I've picked out my favourite one to show you. There are many. The sun produces maybe 5 eruptions a day around solar maximum, which is where we are now. This one happened a few years ago. So we're looking at images of the sun's corona, its atmosphere, taken using the extreme ultraviolet light that's being emitted. So the plasma here has a temperature of maybe 1 or 2 megakelvin. And if we zoom in to a particular part of the sun, and then also run the images through a filter that allows us to detect the edges and the structures in the magnetic field, or strictly speaking, the plasma, which is sculpted by the presence of magnetic fields, we can get these kind of observations. So all of the gas that you see here, all of the plasma, is taking on the shapes of the magnetism that threads through the atmosphere of the sun, the origin of which gets studied here at Leeds. So I won't talk about the origin, but you can ask Steve afterwards about that. So, coronal mass ejections, what do they look like? Well, if we take our series of images and we run them over time, we see that the sun produces enormous events. So bear in mind, the sun is as wide as about 110 Earths lined up side by side. So these are very significant eruptions. In this particular case, much of the plasma escaped the sun, and the magnetic field with it, but much of it fell back to the surface, pulled back down by gravity. You can see where the plasma blobs come down, there's compression and heating, so the gas lights up. There's a whole load of fluid dynamics in here, I'm sure, that I am not equipped to talk about because that's not my area, but the fact that it looks like ink droplets moving through a liquid I find really interesting. So there's probably all kinds of shear flows and interesting effects that this audience would be particularly interested in. So I'd urge you to have a look at the papers around that. But you can go online and you can find movie after movie of amazing eruptions that the sun has produced. This is another coronal mass ejection being launched from the sun a few years ago, leaving what's known as a solar flare in its wake. So that brightening left in the lower atmosphere of the sun is another product of the rearrangement of the magnetic field, which is ultimately driving these eruptions into space. So there's a huge amount of energy that gets released from non-potential magnetic fields in the sun's atmosphere. And on the one hand, that energy powers the eruption, and then back on the sun, it powers the solar flare. So the reconfiguration that's happening here is being driven by the process of magnetic reconnection, where you can diffuse magnetic fields through plasma and change the connectivity and the configuration of the field. And I want to have a look at the implications of that a bit more later on. Just to show you then what our coronagraph data look like today, they are quite different from the fuzzy blobs that we had in the early 1970s. This is the previous event shown using the Solar Dynamics Observatory data, but also a coronagraph series of images from the SOHO spacecraft, which are the kind of orange images. And in those, you can see the full ejection of the plasma into the solar system. So we see a lot of structure, all indicated to us by light from the surface of the sun, which is being scattered by electrons trapped in the magnetic field. So we call these events coronal mass ejections, but one of my colleagues working in the US always likes to say we should call them coronal magnetic eruptions, because actually it's an eruption of magnetic field that's taking place, and the frozen-in plasma in that magnetic field is being taken along for the ride. And there are, movies after movies showing how active and dynamic the sun is. This is a movie actually made, over 20 years ago now, from October 2003. But it just shows how violent the sun can look when you see it in these data sets. So you can see there are eruptions of plasma coming from the sun. You might see the flashes of the flares back on the disk of the sun in the lower atmosphere. And then you see a snowstorm effect starting. And that is caused by high energy particles which are accelerated in shocks driven by the coronal mass ejection. So like this event here. So when we're thinking about the sun as this magnetized fluid, we want to link the evolution of that object to this kind of activity. Why is the sun producing such dynamic events over time? And what's definitely been, I think, a really kind of profound outcome of the space age and studying the sun in this way is how it shifted our perspective of our local star and our relationship with our local star. So I talked about space weather being important, but actually there's a kind of another level on top of that. And that's shown, I think, quite well by this series of images. So what we have here is a series of images taken with two spacecraft called Stereo. The Stereo spacecraft were put into orbit around the sun. So one left the Earth, and let's say the Earth is where you are and the sun here, and one trailed the Earth in its orbit so that it kind of fell behind us and then looked back at the Sun-Earth line with the Earth on the right and the sun on the left. The other spacecraft went faster in its orbit around the sun than we move, and so it looked back and saw the Earth on the left and the sun on the right. And then those two perspectives are put together here. So if I label, we've got the sun in the center, and we've got the Earth appearing twice. So these data sets show us the space between the sun and the Earth. And when we run those images over time, you can see that these eruptions propagate away from the sun, they reach the Earth. But there's also this general outflow from the sun, which is its expanding hot atmosphere in a flow that we call the solar wind. So we're really living inside the atmosphere of the sun. And it's a kind of stormy and variable place. And that's why space weather is such a sort of big concern for us in recent times. So we have ejections from the sun, which is what I'm going to talk about more in a minute. We have these energetic particles that get accelerated out, and we have these flashes of light called solar flares. And for anyone who wants to know more about space weather, you can look up some of these kind of effects. So I've just sort of done a summary here of how these different forms of solar activity impact us here on the Earth, and then have a knock-on effect on our technology. So whether it's radio communications, mobile phone network issues, atmospheric heating that causes the atmosphere to expand, and then all of SpaceX's Starlink satellites to start to deorbit, which has been happening, or satellite charging. There's a whole range of effects. So for people working in this area, it's a real opportunity to work in education and then work with different sectors to help them understand how we go from basic solar physics into space weather forecasting into mitigating the risk for your company. Okay, So what I really want to talk about, though, is what's driving all of this activity. And for that, of course, we have to be thinking about magnetism. So here we have two movies of the sun. On the left-hand side, we've got the visible light images of the sun, so showing the photosphere. This is the disk that we will see in the daytime. And on the right-hand side, the magnetic field, which is threading through that layer of the sun. And the color coding is that the white patches show magnetic fields which are directed towards us along the line of sight, and the black patches show magnetic fields which are the opposite, pointing into the board along our line of sight. So you can see this complexity of magnetism across the surface of the sun. So these images have taken sort of over the last week, so you can see, well, it is shown that the sun is very active at the moment in its maximum of its activity phase. So we have fluid flows of the sun and the magnetic fields threading through. So I just wanted to kind of reinforce that point by superimposing on those images modelled magnetic fields. So we can take these surface measurements or estimations of the magnetic field and then extrapolate them into the corona, the atmosphere above, to get an idea of the strength and direction and configuration of those magnetic fields, and then make these kind of images. And again, these are all really easily and freely available. So you can see that there are concentrations of the magnetic fields where we've got these black and white regions on the surface of the sun where the magnetic fields are the strongest. But what I find interesting is the dynamic side of this. So I want to zoom in now to one of the regions on the surface of the sun and play that as a movie. So this shows how those surface magnetic fields are changing over a few hours. There's a clock running at the top. And because these magnetic fields are threading through a fluid, which is, as we've nicely heard already, in turmoil with convective cells bringing up hot gas, redistributing the plasma on the surface of stars, of the sun. The high plasma density in this layer of the sun has enough energy to be moving these magnetic fields around. And so we have some strong regions where there's sunspots in the middle, and then this weaker kind of network field around it. And magnetic flux comes from inside the sun, becomes always buoyantly lifted up through the surface into the atmosphere, and this is the intersection with the surface. So what's special about, or what's important for solar activity, is that you have these fluid flows, the convection, the rotation, the meridional flows, the different components which are basically evolving and moving these magnetic fields around. And our challenge is to understand how they do that in a way that leads to these forms of solar activity. So these flows in the surface of the sun, in the photosphere, are then directly feeding up into an evolution of the magnetic field in the atmosphere of the sun. So on the right-hand side, I've got corresponding images in EUV, so showing the hot plasma, and showing the magnetic structures as revealed by the plasma structures and how they're changing over time. And you can see there are these loops, there are these dark structures that we call filaments, but it's very dynamic, as you would expect, because the magnetic field is always moving around. And as it's moving and evolving, it gets distorted, and energy is injected into the magnetic field, which can then be available to be released. So when we look at images like this of the atmosphere of the sun, we see plasma arches. And that plasma is frozen into the magnetic field, so it can't get off the magnetic field easily. It's constrained to move along the magnetic field structures. So for observers, it's natural to think, well, this is the kind of fundamental unit of magnetic field in the atmosphere of the sun, these loops. But when it comes to eruptive activity, there is a different magnetic field configuration which is invoked in theory as being the one that is important for coronal mass ejections. And that's something called, or that we call, a flux rope. So you could think of it in different ways. I like to visualize it as being a series of magnetic fields which are helical, so twisted around an axis You might think about it as a volume current running through the atmosphere of the sun. And magnetic flux ropes are of interest theoretically because if you look at the forces on these structures, for example, a curved one, which is rooted in the atmosphere of the sun, you have a tension force which comes from that curvature. But because the field lines are helical, you have a magnetic pressure gradient. And whereas the tension force points down, mostly, the pressure gradient points up. So you can get this competition of forces in your flux rope, which could be balanced and could mean your flux rope is stable, or they could become unbalanced in a direction that means this eruption or this structure gets erupted into the solar system. So to illustrate that, I've just got a couple of simulations by colleagues Bernard Kleem and Tibor Turek to show that. So this is an idealized flux rope. You can see the rainbow colors and the helical structure with some more potential field overlying it. And if you build your flux rope in such a way that you're increasing the pressure gradient up, you may get to a point where the overlying tension or the tension of the overlying field is not sufficient to hold your flux rope down. And in that case, it will erupt up into the space, into the solar system. This is an instability called the torus instability. So this is a plasma physics instability. People in this room may know this in more detail than I do if this is the kind of thing that you work on. But it's found an application in solar physics in recent years. So there's a lot of focus on looking at could the torus instability be taking place in the atmosphere of the sun if flux ropes are indeed present also in the atmosphere of the sun. And what you need for this is an overlying magnetic field which falls sufficiently rapidly with height so that your flux rope is no longer held down. There's another instability that was quite popular for a time in solar physics called the kink instability. This is a simulation by Tibor Turek, where now we've got a really twisted flux rope, so twisted that when it becomes kink unstable, it converts some of its twist into a distortion of the axis of the rope itself, and it rises up. This received a lot of attention in the solar community because on the left-hand side, you can see the origins of an eruption on the sun, which just really nicely matched the simulation. So it's quite compelling that these instabilities, or this one in particular, could be happening on the sun. We don't see this very often, I have to say, as in kinking structures that are rising up, but there are observations that support that this is happening. So the work that I do, and that I want to talk about in kind of the next 15 minutes, is to try and convince you that flux ropes do form and exist in the atmosphere of the sun. So this is a kind of contentious piece of research. People tend to fall into two camps. We have the pro-flux rope camp and we have the non-flux rope camp. So depending on the audience, I might get a warm round of applause at the end, or I might get scowling glares because I've said the wrong thing. I've had both. I like both. I like the challenge. So I want to show you some observations of plasma structures in the atmosphere of the sun that are suggestive that we do indeed get flux ropes, twisted magnetic fields forming in the atmosphere of the sun. And we have to be guided by the plasma structures because we don't yet have observations of the magnetic fields directly in the atmosphere of the sun, only at the surface. So it is hard to directly identify these structures. So I'm going to show you a cartoon which originated in 1989 by Ard van Baarle-Hoyen, and these kind of cartoon field lines I hope will convey the process by which you build up a flux rope in the atmosphere of the sun, potentially. So we start with two field lines, so I hope you'll excuse me using the concept of field lines. So here we have, coming out of the surface of the sun and back in again, two field lines. But we know the surface of the sun is moving, and sometimes the flows are chaotic, and sometimes the flows are more organized. So let's say we have an organized flow in which we take our foot points and we shear them in a common direction. And then let's say we have another flow which takes our foot points and brings two of them close together. So the foot points ending in B and C. In this case, in the right conditions, you can invoke magnetic reconnection, which will break and rejoin those field lines in this cartoon concept. So now we change our connectivity. So we go from two field lines going from A to B and C to D in the top right. Now we've got a longer field line going from A to D and a short one going from C to B. And if that short field line is indeed short enough and curved sufficiently, tension will pull that below the photosphere and it will disappear from the layer of the sun in which we're measuring it. So it should just vanish. Meanwhile, in the atmosphere above, a longer and more sheared structure should start to build. And if you go through this process again and you bring in some overlying field and you reconnect it again, you can, if the reconnection is low down, start to build up helical field lines about an axis. So this cartoon shows a way that with the right surface flows, the right fluid flows, plus reconnection, you could reconfigure your field and go into a flux slope configuration. So do we see that? Well, okay, let's have a look at some fluid flows or magnetic fields being moved around by fluid flows. This is a zoom in of a CME source region. So white is magnetic field coming out towards us, black going into the sun. This magnetic structure has emerged from below the surface and is being moved around. And you see how the white and the black come together and then they disappear. So this would be the product of little loops being formed and being pulled by tension below the photosphere. So these observations are in support of this cartoon process. So let's have a look at the atmosphere. What's happening above? So to see the atmosphere above, I need to use a different data set. For example, soft X-ray images or EUV images that show the hot gas trapped along the coronal magnetic fields. So let's start with our observations of loops. Okay, this is a top-down view of the same region I just showed you in the photosphere. And now we see the plasma loops from above. I hope you feel convinced that if you look down from above onto loops, this is what it could look like. But let's see the evolution. So then we need to shear our foot points and see a corresponding change in the angle of my loops above, which we see. I keep the process going, I undergo some reconnection, I build up longer field lines containing plasma which is even more aligned north-south, and then I keep going and I build in my helical field, and if I have around one turn and I look from above, the plasma tracing out those magnetic field lines should look roughly S-shaped, which is what we see. So this kind of cartoon version, which actually is backed up by simulations, seems to be taking place in the atmosphere of the sun over a few days in advance of a coronal mass ejection happening. And not only can we look at these kind of surface flows which are bringing flux together and reconnecting it, we can also look at other surface flows, or have seen other surface flows, where fragments are orbiting each other and driving reconnection and building up these S-shaped structures. So let's have a quick look at one of those. This is another region on the sun. Let's zoom in. Let's see if I can run these two simultaneously. Oh no, they don't run simultaneously, sorry. So this is a CME source region in the hours up to its eruption. We see some energy release and brightening of the plasma. Then it fades, and there is a faint S-shaped structure that forms, and then it erupts. But it's hard to see. I'm going to show it more clearly in a second. And this eruption was driven by fluid flows actually associated with magnetic flux coming up through the photosphere, which it does in a fragmented way, and these fragments kind of rotated around each other, and that we think drove reconnection to build these helical field lines. So there's a big open question in solar physics to really better characterize these fluid flows, to understand which are the right ones that build the flux slopes that lead to an eruption. So the important aspect here, which is hard to see, is that about an hour or two before the eruption takes place, a very faint S-shaped structure forms as a product of reconnection, and it's that structure that erupts. So again and again, when we look at the atmosphere of the sun, I would say the observations are quite compelling that magnetic flux ropes are building. But we have other techniques, not just looking at plasma structures, to try and understand what the configuration is. So in this data set, the magnetic field that's measured at the surface of the sun is a vector measurement. So we have the full information about the three-dimensional field in that surface layer. So we can look at reconstructing that magnetic field above using that data set to see what is the field configuration like in the volume. And there are certain techniques that are available in the community. And the one that we use to analyse this event is a piece of code by Gerardo Valori, who currently works in Germany. So this code will take the vector field in the photosphere and allow you to reconstruct the magnetic field in the volume above. And when we did that for this event, we saw this in our data. So I think this is a movie that spins around. Yes. So, okay, we felt quite convinced that we would find a flux rope because of the plasma emission structures which are tracing out the magnetic fields. But it was nice validation then in the extrapolated volume to see this. So it's actually quite a high flux rope compared to what people normally find in the atmosphere of the sun. I hope you can see it has a handedness, a twist to it. So it has a right-handed twist to it. Roughly one turn in the magnetic field, and this flux rope really well matches the observations that we see in the plasma emission structures. And then once you've got your extrapolation, you can do some numbers. What's the flux? What's the electric current? What's the altitude of the flux rope in the atmosphere? And you can also go back to what I was talking about earlier, which is to look at some stability measures. So you can look at this flux rope and the height at which it's at in the surrounding magnetic field, which we didn't show in the previous snapshot, to see, well, how stable is it? And this one, to cut a long story short, seems to be in the realm of when the torus instability might kick in. So the fact we found this flux rope and it erupted a couple of hours later would also suggest that this was a kind of marginally stable flux rope. Okay, so I wanted to just quickly flag up two missions which have been really important for solar physics in the last few years and make reference to how they're helping us understand flux ropes and coronal mass ejections from the sun. So the first mission is Solar Orbiter. And to show you where Solar Orbiter is, I've got a top-down view of the solar system, just the inner solar system, sun at the center, with Mercury, Venus, Earth, and Mars, the planets, with a kind of smattering of the spacecraft we use. So we've got near the Earth, the Japanese mission Hinode that I talked about, the SOHO mission that I talked about, SDO, and then the two stereo spacecraft which are in orbit around the sun. Solar Orbiter is a groundbreaking mission because it goes so close to the sun, gets to the same distance as around Mercury does, and it carries with it telescopes that can take images of the sun. So it needs a fantastic heat shield to be able to protect it from the intense radiation at that point, and our telescopes kind of peek through the heat shield. But there are also instruments on board that measure the magnetic fields and the plasmas that move over the spacecraft. So with Solar Orbiter, we can get very close to the sun and measure these eruptions shortly after they've left our star. And there was a nice event just to kind of illustrate the power of the spacecraft that took place back in 2022. So that's the birth of the eruption. But before the eruption kicks off, there is this nice plasma flow that kind of snakes across the sun. And a colleague of mine analysed that plasma flow, and it has a kind of helical nature to it as you watch it propagate across the sun. So the helical flow, it must be guided by magnetic fields, which would suggest to us that you have helical magnetic fields or that you have a flux rope in that part of the sun. So that was a really nice observation. But not only do we have the Solar Orbiter spacecraft that goes into about the distance of Mercury, there is another spacecraft. So Solar Orbiter is a European Space Agency mission. NASA, of course, want to go on better, and they have their Parker Solar Probe, which goes about 7 times closer to the Sun than Solar Orbiter does. So this is an animation showing where Parker Solar Probe is. And you may have seen in the news around Christmas this very close flyby that the spacecraft had with the Sun. So to give you some context, Solar Orbiter on its sunward side heats up to about 500 degrees Celsius. Parker Solar Probe heats up to about 1500 degrees Celsius. So it's getting incredibly close. So it cannot look directly at the Sun, but it can measure the flows coming out from the Sun washing over the spacecraft. And it can look to the side of the Sun. So it gets close, but it's limited in what it can actually do. So here we see Parker Solar Probe doing its journey around the Sun and getting in incredibly close. And the reason that I wanted to show the previous Solar Orbiter data set is that eruption from the Sun was also picked up by Parker Solar Probe. It washed over the spacecraft and kind of came by the spacecraft so we can see it. And I love this data set. So this is the Whisper camera on Parker Solar Probe. This video contains a lot of information. We've got the Sun on the left-hand side, and you'll see the Sun changing in size as Parker is getting closer and further away. You'll see the speed of the spacecraft, which reaches 160 kilometers a second in this time snapshot that we're looking at. So, okay, I'll put it in old money as well, 360,000 miles an hour. It's because this is from a public engagement talk, so it's got imperial and metric in there. And then the black and white is basically our coronagraph. So the Sun is blocked out, and you can see the scattered light coming from structures in the atmosphere of the Sun. But for this one, we're particularly interested in what's leaving the Sun, the coronal mass ejection. So it's incredibly close to the Sun at this point, only 40 solar radii, so getting really close, and you can actually sort of start to see the build-up, and then the coronal mass ejection should come through, bam! You may even see the concave up bit of the flux rope going through there as well. You might see the Milky Way, and there's also a comet's tail that comes through at some point. I always forget which point in the movie it is. So Parker Solar Probe works in a highly complementary way to Solar Orbiter, so that we can get close up to the Sun with Parker, kind of close but not as close with Solar Orbiter, and then if we're really lucky, we might have an alignment that means we can pick up these eruptions when they get to the Earth, and we can pick them up with the telescopes there. So this was a really nice event where we looked at the flux rope on the Sun, and it was measured directly by Parker, directly by Solar Orbiter, and there was a nice study looking at how the expansion of the flux rope proceeded, how the solar wind around the flux rope created drag and distorted the flux rope, and it's those kind of studies that we need to know to kind of fill the missing links that we've previously had from looking at the Sun and then knowing what reaches us and drives space weather at the Earth. So I've only got 2 more slides now before we can go on to take some questions. The first was just to kind of have a summary to say that I think there's pretty compelling evidence that helical structures, current-carrying, energy-storing structures in the atmosphere of the Sun are forming, driven by fluid flows in the surface of the Sun that evolve that magnetic field, coupled with reconnection. And we're seeing more and more evidence, I would say, before coronal mass ejections. And actually, these flux ropes can form in a series of heights in the atmosphere of the Sun, which is important because that affects the stability of the structures and how long they might be on the Sun for before they erupt as a coronal mass ejection. So that's just a kind of flavour of one particular piece of research that we're working on at the Mullard Space Science Laboratory. But then my final slide actually has nothing to do with coronal mass ejections at all. It's just a really nice movie of images taken by the Extreme Ultraviolet Imaging Telescope on Solar Orbiter, which at one of its close approaches to the sun took some lovely observations. Oops, oh no, I've come out of my presentation. Of the sun's south pole. So here we're highly zoomed in. You can see how dynamic the atmosphere of the sun is. You can see the clock running on the bottom left-hand side. There are jets of plasma, changes all the time, heating events. I just like this because I kind of feel like I'm close to the sun and sort of underneath it, looking up at it. And I thought that was a nice sort of moment for us to end the talk on. So thank you for listening, and I'll take questions.